All right, welcome everyone. Today we're going to be doing lesson 13, which is where we see some applications of integration. And then this will be part one of a two-part lecture. All right, so you may remember back in Calculus 1, once we finished learning about how to take derivatives, we began seeing things that we could actually do with derivatives. Like we saw a lot of these related rate problems, optimization problems, physics with velocity and position, everything kind of like that. Now we're going to be doing something similar with integration, and I guess we've already seen some applications. We've seen finding volume as an application, but today we're going to be branching off into another field, specifically physics, and we're going to be seeing how integration can help us in that field right here. All right, so what we're going to do for physics, our physics application, is going to be computing work. All right, so loosely speaking, work is the amount of energy a force expends in order to move an object a particular distance. Does anyone happen to know the formula for work? Work is equal to what? It's going to be force times distance. So we have the force that we are applying and then the distance that we are applying the force. Okay, well, I mean, if we know what the force is, we know what the distance is, we can throw those two numbers in there and we get work. So what does this have to do with integration? Well, the thing is that this formula only works for constant force, meaning that we're applying the same force over the entire distance. But maybe we only applied maybe we applied a larger force to begin with and then maybe a smaller force as we continued onwards. So how much work would we be doing in that case? And this is where integration comes in. Our new definition for work is going to be the integral from a to b of f dx. So why do we have this definition? Why did we have an integral and then now we have a dx here? Well, what we're doing is we're computing the work to move a tiny distance. So we have a constant force times the tiny distance. And then what we do is we're adding together all of these little chunks, and just like it worked with volume, it's going to end up combining and giving us the total amount of work that we're going to do. So we have all these little kind of micro works that we're computing where we exert a constant force over a tiny distance, but then maybe each tiny distance we go, the force is changing. So that's kind of how this is going, and this is where the formula comes from. So let's take a look at an example of this. Okay, so find the work it takes to pull a dangling chain of length 5 meters and a mass density of 4 kilograms per meter. I'll explain what that means in a moment. Up over the side of a tall building. And by tall, I mean the height is greater than 5 meters. So this way that the chain is entirely hanging off the side and none of it's kind of like piling up on the bottom because the building is too short. All right, with any kind of applied problem, both the volume ones we've done before and then these new physics problems, I highly recommend that we draw a picture. So let's say we have our tall building here, right? And we have our person on the top, and there's the chain. So here's the chain right here. And so it extends down 5 meters, but the building is longer than that. And we want to figure out the amount of work it's going to take to pull all of this chain up over the top of the building. All right, now what does this mass density mean? Mass density is how much the mass the chain has per unit meter. So what this is saying is that 1 meter of chain has mass of 4 kilograms. That's what this is saying right here. And the unit for this is kilograms per meter. So just to make sure we understand this, how much or what's the mass of the entire chain going to be? Yeah, it's going to be 20 kilograms. That's right. Yeah, it says tiny distance right here. That's right. So it's the work we do over a tiny distance for this part. But yeah, the mass of the entire chain is going to be 5 meters times 4 kilograms per meter, which will give us 20 kilograms. And for those of you in a science class, you can see that the units will cancel out here with meters, and then we just end up with kilograms right here. So however long our chain is, we simply multiply that by 4. That's the mass of it in kilograms. Okay, now what we're going to do, just like all of the other problems we've been doing with integration, is we're going to break up our integral into tiny pieces. So what we're going to do is we're going to like kind of zoom in on a tiny piece of chain here. Okay, so we're zooming in on that. And we want to figure out how much work it takes to move one tiny section of chain. So we're breaking this chain up into a bunch of different pieces. They're going to be very, very small pieces of chain. And we're going to figure out how much work it's going to take to move up that little chunk of chain. And then how much work is going to take to move up a chunk of chain maybe up here. And then we're going to add all of those together and we get the whole chain. That's going to be the total amount of work. Okay, so let's just suppose we have like a random piece of chain that we pick. So let's say we pick it right here. Now let's say this, the distance down from the top of this chain is going to be y. All right, so that's going to be y meters from the top. And then if I want to have a very, very short piece of chain right here, what do you think I'm going to call that? The length of that? dy, right? Anytime we have something tiny in a particular direction, like in the y direction right here, we're going to call it d, whatever the variable is. So the length of this chain is going to be dy. All right, now let's figure out the amount of work it takes to pull this piece of the chain in particular up to the top. So the work for moving this tiny chain up, well, work is equal to force times distance, right? Now, what force are we fighting against when we're moving the chain up the building? Gravity, right? So this is the force due to gravity. As anyone who's taken physics or even high school physics, do you guys remember what the formula for the force due to gravity is? mg, that's right. So the force due to gravity is the mass times the gravitational constant, g. Now I'm going to say right now that we're going to have some physical constants in here like g, and then we're also going to have like the density of water later on. Don't worry if you don't know what those are. All of our answers will either just get rid of those or just leave them as part of the answer. So like a g in your answer. So don't worry if you don't know the g is like 9.81, whatever. That's not going to be relevant here. We're just going to leave that for physics. All right, so anyways, our force due to gravity is mg. Now we said this variable y is the distance we need to move the chain up to the top. So this is mgy. Okay, now g is a constant, y is a variable we can integrate with respect to. The thing we can maybe get a little bit more specific about is the mass. So remember, the mass is the mass density, which was 4 times the length of the chain, right? But what was the length of the chain? It was dy. That means that the mass of this chain is going to be 4 dy. It's dy meters long right here, and it has 4 kilograms per meter. So this is going to be our mass. And if we put this in a more pleasing order with dy at the end, we figure out that the work it takes to move this little piece of chain up to the top is going to be 4gy dy. And let's think about this. This actually kind of makes sense, right? Because the further down the chain is, the more effort we need to expend to bring that piece of the chain up. Like, for example, a chain at the very top, that's going to be really easy. Just kind of yoink it up and you're done. But something further down, you're going to need to lift it all the way up here. So you're going to expend more effort doing that piece of the chain. All right. So now that we've done the work on one tiny piece of chain, we're going to add together all of the work for all of these little pieces of chain. And that's going to give us our total work. So our work W, like it's just going to be a total, is going to be an integral because we're adding all of these together. Okay, now let me ask you guys this. What do you think the bounds of this integral is going to be? Yeah. Yeah, that we would just say 0 to 5. But yeah, you're right. Yeah, so it's going to be 0 to 5. We always put it in like the proper order. But yeah, that's right. So we have the integral from 0 to 5 right here. And why is that? Well, because our chain links start at 0 up here, and then they extend all the way down to a length of 5, and then they stop. So remember, this is something I said last time too. The bounds of your integral is always wherever the object is of whatever problem you're doing. So the object in this case is the chain. It starts at 0, and then it goes down to 5. All right, and then now we just have to do this integral right here. Let's see, 4g is a constant. So we're effectively just doing y dy. Well, the integral of y will be, equal sign, y squared over 2 from 0 to 5. Let's see, so this is 2gy squared from 0 to 5 here. And then I'm going to put 5 in here. And I got 25, and then times 2 will be 50. There we go. So we're going to have 50g as our answer. And it's okay. Again, it's okay if you don't know what g is. We're just going to leave it there. And then does anyone happen to remember the unit for work, the SI unit for work? Anyone know what that is? Yeah, it's joules. That's right. So if you're someone that likes to include units there, we would put J for joules, which is also a unit of energy. So there we go, because work is a change in energy. So that's why it has the same unit right there. All right, there we go. So there's an example of using an integral in a work problem right here. Now, why couldn't we just use force times distance? We know that the mass of this was 20. We could multiply that by g, and the distance we need to move the chain up would be 5. Why can't we do that? Well, the problem is that different pieces of the chain need different distances to move them up. So for example, the work done on this piece of chain is going to be a lot less than the work done down here. So we can't just use a uniform number for this because each piece of chain needs a different amount of work. All right, so why don't you guys try this? This is going to be like pretty much exactly the same problem, only it's going to have some different numbers here. So practice 1. So find the work it takes to pull a chain of length. Well, this time it's going to be 7 meters and a mass density of, let's see, 3 kilograms per meter this time, up over the side of a tall building. We're literally doing the same thing that we did before, only this time we're doing a length of 7 meters and then a lower mass density here. Why did we use 4 instead of 20 for the mass? Well, remember, the mass density of the chain, for every meter of chain we have 4 kilograms worth of mass. Now, for this problem, remember, we're not doing the whole chain, we're doing the tiny chain. And the tiny chain had a length of dy meters. So the mass of that little tiny piece of chain, I guess I should write m tiny maybe, is going to be 4 times the length of the chain we're talking about, which is dy in this case. Yeah. So the question here was that in order to get the specific numeric value for this, we would need to plug in a particular value for G, which is 9.81. And then we would end up getting a constant if we multiply by that. Why would the work be a constant? We're effectively measuring how much energy it takes to do something. So we're kind of viewing this as one task. How much effort do we need to exert in this one task of bringing all the chain up? And it's going to be whatever number that is. Can our integral bound in physics problems be negative? I mean, it depends on the situation. For this problem, I should have mentioned this earlier, but y is going to start at 0 up here and then increase downwards. So remember, y is the distance from the top. So if we're 2 down, that means y is going to be positive 2 right here. And defining y to be 0 at the top of our problem and then making it increase as we go down, that's going to be something we're going to do like pretty much all the time. That's usually how we're going to do things. It makes things easier that way. (147g over 2). We'll see. So d is the same as y. Yeah, that's right. You're moving up the distance of y. That's right. All right, I need to make sure we have time to get to some of the other problems here. So I'm just going to go ahead and start doing these here. So this problem is going to be almost exactly the same, only we just have a different length of the chain and then a different mass density. But we're still going to solve it the same way. We're still going to figure out the work on a tiny chunk of the chain, which is the force we do on it times the distance we move it. The force is once again going to be gravity. And that's probably the most common force that we're going to be working against in these problems. And then if we set up everything in the same way that we did with the previous problem, the distance we're moving this up is going to be y. So we're going to have mgy. And then finally, this is the strange part. Remember, the mass of our tiny length of chain is going to be 3 kilograms per meter times how many meters the chain is. Well, how many meters is this tiny piece of chain? It's going to be dy. So we're going to have 3 dy. That's the same thing as m. And we're going to have gy. And then if we rearrange this to a nicer order, we have 3 gy dy. And that's the amount of work it takes to move up a tiny amount of chain. Oh, choose your fighter. You forgot to include pi squared as one of those as well. That's a common approximation for G. Don't tell a physicist that, though. They'll get mad. How to use 10? Yeah, sometimes 10 is good enough. I mean, depending on what your application is.
Professor?
Yeah, what's up?
So on the previous example, you said the mass of the entire chain is 5 meters times 4 kilograms per meter, and you get 20 kilograms. Why would we use that?
Well, we didn't actually end up using the fact that it was 20 kilograms total. I just used that as an example to make sure we understand the mass density. So we didn't need to know that the whole chain is 20.
Okay, gotcha. Thank you.
All right, so this is the amount of work it takes to move up a tiny amount of chain. So if we want to move up all of the chain, we throw it into an integral. Now this time, remember, we need to always have our bounds be wherever the physical object is. So we start from 0 meters down from the top. And since it's a 7-meter chain, as low as we can go, our max distance from the top is 7. So we have the integral 0 to 7. We integrate the y to be y squared, divide by 2. Have this be from 0 to 7. I plug 7 in there. giving me 49. And 3 times 49 is 147. So we end up getting this somewhat bizarre number, 147 over 2 joules here. By the way, don't worry about the units. We don't have written homework, so you don't need to worry about that. But I'm just putting that there for people that like to know what units something is. All right. Why does gy change to? I just rearranged the order I was multiplying here. So I just moved the dy to the back. That's all I did right here. So I'm just changing the order I'm multiplying things in. All right, let's move on to another type of problem here. So let's see here. Find the amount of work it takes to stretch a spring of constant, spring constant, K equals 1,000, 5 meters from its equilibrium position. Okay. Now, all right, so we needed to know a few things from physics here in order to do this. And so one thing I do want you guys to know off the top of your head is that the force due to gravity is the mass times the gravitational constant. So I do want you to know that. I also want you to know that work is force times distance. So I want you to know that. But if we do any other kind of force other than gravity, we'll provide you with the formula for that. So I don't, for any, like if we're doing a spring or some other random force, then we'll give you what that is. The force exerted by a spring that's being stretched is negative kx, where x is how far it's being stretched from equilibrium, and k is this constant right here. Okay, so what we're going to be doing for this problem is we're going to use our formula for work. So our formula for work now is force times moving a tiny little distance. Now, we got to be really careful here, and I probably should have written this differently in the worksheet if I'm being honest. So this is the force that the spring exerts, right? So the reason why it's negative kx is, let's say we move in the positive direction, right? Like let's say we move 2 in the positive direction. The spring doesn't like that. The spring wants to move back to where it came from, right? That's why springs kind of stretch or compress and then they want to bounce back. So the spring is going to work opposite to the direction we're moving. But the force that we are applying on the spring will be positive. If we apply a force of kx, we're counteracting the spring's force and moving in that direction. So we're going to end up getting positive kx. And another thing I'm going to say about work for this class, negative work actually is a thing. It makes physical sense in order to have, you can have negative work. We're not going to do that though. It's a little bit confusing, but don't worry. All of your answers for the work problems. So in this class, work will be greater than or equal to 0. In physics class, you'll talk about what negative work means, but for here, we're not going to deal with that. So we're going to use the positive version here. Now, what we're doing is we're stretching this spring from its equilibrium position. So let's say that's 0. So kind of like from its default position, all the way to 5 meters away. Remember, this x is the distance from equilibrium. All right. So then now all I have to do is integrate this. Now this is a constant, and then this is a variable. So we have k x squared over 2, 0 to 5. Well, I guess we could plug in k as 1,000. So 1,000 over 2 will be 500. So we have 500 x squared, 0 to 5. And then we plug 5 in here, which will get 25. 25 times 5 is 625. So we have quite a lot of joules of work needed to pull this spring from its equilibrium position. pretty much the spring constant, what that means physically is the bigger the spring constant, the stiffer the spring is. So like it's going to strongly resist being stretched out or compressed as well here. You were right. So it's not that much work. Thank you very much. All right, so it's actually 12,500 joules, my mistake. All right, so there's that kind of problem. Let's see, how are we doing on time here? I'm gonna skip example 3. Example 3, honestly, is kind of dumb. I don't know why I put it in here. But I will write up that for later. So if you guys want to see another example, and this is another chain example, then I'll write this up and put it for you guys later. What I really want to do is I really want to get to the last type of work problem that we're going to be doing here. Let's scooch this up. All right. So what we're going to do is we're going to find the amount of work it takes to pump fluid from a container. So I guess this isn't as relevant in Florida, but say maybe you're up north and you want to drain your swimming pool for the winter. So you're draining your swimming pool and the pump's doing an amount of work. How much work does that pump need to exert? How much energy do you need to supply to the pump in order to get all of the water out of the pool? And we're going to be kind of answering questions like that with different shaped containers. And it turns out the shape of the container and how big it is going to change how much work it's going to take to move all of the water out right here. Yeah, I guess, yeah. We're in. Okay, yeah, maybe we do that in Florida as well. So sorry, I was just talking at my ass. All right, let's go ahead and do this anyways. So let's see, example 4. Find the amount of work it takes to pump all of the water over the top of a full cubic tank of side length 2 meters. All right, so let's go ahead and draw this here. So here's our cube. Well, our approximation of a cube. And this cube is entirely filled with water. So it's like kind of bursting to the brim. We have all this water up here. And each side length is going to be 2 meters right here. Remember, you guys you don't need to draw a picture, but you should. I strongly encourage you to draw a picture for each one of these. Now, we're going to kind of apply the same philosophy we've been doing for integrals to this problem. So the philosophy we've been applying so far is we break up our problem into a bunch of tiny pieces. We figure out how much whatever it takes for each of those pieces, and then we add all of it together. So whether that's volume or work, it's the same kind of thing. Anytime you're adding a bunch of tiny pieces together, that's going to end up forming an integral. So what we're going to do is we're going to imagine that, let's say we almost take like a slice of water here. So let's say we have like this square right here, and it's a very thin slice of water. Now, what we're going to do is we're going to figure out the amount of work it takes to move this particular slice of water up and over the top. Because what force are we fighting against for this one? Gravity, right? You know, water is pretty heavy, so we're fighting against the force of gravity. So we're doing the force times the distance. So we're going to do gravity, which is mg of our distance. Yeah, so we're just going to see how much work it takes to move this slice over. And then if we add the work for all of the slices together, then we're going to get our total amount of work. We also have a buoyant force pushing the water up. We're just going to assume that gravity is the only thing here. We're not going to complicate things at all for this. All right. So now what I'm going to do here, I'm going to do the same thing that I did for these chain problems earlier. I'm going to define y to be 0 at the top. It's going to increase downwards. So y is the distance from the top. That's what y is going to be. All right, so then that means my distance is just going to be y. And that's why I set it up that way. So I could just put in a single variable right there and be done with the distance half of this. Then I just focus on the force part. All right, so g is a constant. Y is something that we can have in our integral. But what about m? Well, kind of like how we had the mass density times length for the chain, what we're going to do is we're going to have the ordinary density times the volume for our mass here. So our mass is going to be the density, which is rho. A lot of people like to call this P, but it's kind of like a P where its tail is bent back a little bit. And then times the volume. So this part right here, mass density times volume, that will end up giving us mass right here. Okay, so now density of water, that's a constant as well. This water isn't changing density as we move up and down or anything like that. So this is a constant, this is a constant, this is a variable we're okay with, but we can't just have V in there. We need to have either a constant or Y's. So we need to figure out the volume of each one of these slices. Okay, well, technically this is a very thin rectangular prism, right? So the volume of this is going to be its length, which is 2, times its width, which is 2. And then what's the height of this going to be? What do you think I'm going to call the height of this? dy, that's right. So this is a tiny change in the y direction, so this is going to be dy. So the volume of our slice is going to be 4 dy. What is rho v again? It's the density times the volume, and that's going to give us mass right here. All right, so rho is a constant. 4 dy is the volume of our slice, and then we have gy. And just like before, we're going to put this in a more aesthetic order. So we're going to have 4 rho g y dy. Usually we put constants, then the variable, then the differential at the end. All right, now that was the work on one slice of the water. It sounds kind of weird to say that, but that's literally what's going on. So now if we want to do the total amount of work, we're just going to integrate all of this. 4 rho g y dy. Okay, now let me ask you guys again. This is a skill I really want you guys to develop here. What are the bounds of this integral going to be? 0 to 2, right? So remember, we're moving water. So we want our bounds to be where the water is. So the water starts at a depth of 0, meaning the surface up here, and it goes down all the way to the bottom of the cube, which has a depth of 2. So this is going to be from 0 to 2. All right, so now we're going to integrate this. Remember, rho and g are just constants. And again, I don't expect you to memorize these. I don't expect you to know what rho is for any substance. You don't even need to know what g is. We're just going to leave those as constants. So we're going to have 4 rho g y squared over 2, from 0 to 2. This is the same as 2 rho g y squared. And then if I plug 2 into here, 2 times 2 is 4, and then times another 2 will be 8. So I have 8 rho g, and since this is work, my unit's going to be joules for this right here. So that's how we deal with pumping water out of something, is we figure out the volume of one slice at a particular level right here, and then we figure out how much work it needs to move out that one slice. All right, so now I want you guys to try this. So we're going to do a practice problem kind of similar to this one. All right, density of water is 1. It depends on the units. It's 1 gram per centimeter cubed, right? And then it's 1,000 kilograms per meter cubed. So it depends on which units you're using, but we're not using that at all. You don't need to know any of those numbers. Okay, for the practice problem number 2, I want you to find the amount of work it takes to pump all of the water over the top of a half full, so this is a little bit different, half full cubic container of side length 4 meters. Okay, so this is going to be almost exactly the same as the example we just did, but there's going to be one key difference, and that difference is going to rear its head near the end of the problem. Why don't you guys take a few minutes and try to figure this one out here? I'd be careful, Matthew. Think about where is the water? Two to four? We'll see. That's light. Rho is the density, which looks an awful lot like a P. Well, the slice stuff should be similar to the way we did it here. So we want to figure out the work it takes to move one slice. And that's going to, the work is going to be force times distance. And so you kind of go through the same process, only this time the side length is 4. Rho V. So if you take the density of something, which is mass per unit volume, and then you multiply by how big it is, which is the volume, that will end up giving you the mass. So rho times V, or density times volume, is the mass. Is everything the same but the limits? Well, pretty much. I mean, the side lengths are going to be different, but yeah. Yeah, I don't know if anyone has a row on their keyboard to easily type it. It looks pretty much the same way. Nope, I don't think so, Logan. That looks like a good answer. Seems like we have some disagreement here. 32 rho G, 96 rho G. 16 dy would be the volume. We guys another minute or so, and then we'll see which one it is. Yeah, that's right. All right, let's go through this one, and then I have one more example after this, and then we'll be good for the week. All right, so we want to pump all of the water over the top of a half full cubic container of side length 4 meters. Now we're still going to divide everything into slices. So the water now is going to be right here, but we're still going to take these rectangular slices. And we're going to figure out how much work it takes to move this out over the top, not just to the top of the water here, but like all the way out over the top. So the work done on each slice is force times distance, and the force we're fighting against is gravity. And if we define y equals 0 here at the top and increasing downwards, this will be rho g y. All right, now y is okay, g is okay. Mass, we write as rho times v, or the density times the volume. And then the volume of each slice, well, let's see, the side lengths were 4, right? So this is 4, and then as always, if we have something very thin in the y direction, we're going to call that dy. So we're going to have 4 times dy, or 16 dy. So that will go in right here. And then we get 16 rho gy dy. There we go. All right, so now let's integrate this. So we have 16 rho gy dy. Now, this is where we need to be especially careful. And remember, the philosophy of the, the philosophy of the bounds is wherever the object is. So remember, our coordinate system is y equals 0 up here, and it increases as we go downwards. So where does the water start in this coordinate system? It starts at 2. That's right. We don't have any water up here. It doesn't start at 0. We have to go down 2 until we hit the water. And then how deep does the water go? Well, it goes all the way down to the bottom of the cube here, which is going to be at 4. So this integral isn't from 0 to 2. The water is not somehow like hovering right here, being ready to pump it out. It's sitting here at the bottom. So it's going to go from 2 to 4 for this. All right, so then let's do our integral. We have 8 rho gy squared, 2 to 4. So we have 8 rho g, and then 4 squared is 16. 2 squared is 4. So we have 8 rho g times 12, which is 96 rho g. So that's going to be our solution here. All right, so the moral of this story is be very careful what you put for your bounds. May not be what you think. Let's see here. Oh, why is it 8? Well, I divided by a square here because I raised this to be a y squared, and I divided by 2 to get an 8. All right, I'm going to do one more problem like this, and then we're good. Okay, so find the work it takes to pump all the fluid out of a conical tank, and it's going to be pointing upwards. Of height 4 and radius 2 that is filled to a height of 2. Okay, so let's draw the picture here. So we have an upward pointing cone. All right. We know the total height of it's going to be 4, and the radius at the bottom here will be 2. And they also say that the water, or whatever fluid it is, goes halfway up, or to a height of 2. Note that that's different from saying that it's half full. being to a height of 2, even though that's half of 4, is not saying that this thing is half full. This is actually more than half full based on the shape of the cone. Watch out for that. All right, so what we want to do is we want to figure out if there's water here, we want to pump all of that out over the top right here. So just like before, we're going to use the same philosophy here. We're going to break all of this water into slices and then figure out the amount of work it takes to move each slice to the top. All right, so let's take a slice here. Now this time, since we're not dealing with a cube, our slices will instead be these coin-shaped cylinders right here. So we're going to take these kind of cylindrical slices out of here. All right. So the work on one slice, well, we have the force times distance. The force, once again, is gravity. We're going to define y equals 0 up here and increasing downwards. So we have mgy. For most of these problems, you can honestly kind of just go to here to start with. For mass, we know the mass is the density times the volume of our water. If you aren't doing a what version?
If you're not using like a density or anything, if you're not giving a mass, you just row.
Oh, yeah. So what we were saying here is that if you weren't given like a particular type of fluid or a mass or anything, can we just use rho? And yeah, rho is generally understood to be a density variable. Yeah, so whenever you mean density, that's rho. All right, so whatever, we're assuming that this fluid's of constant density. We're not going to do anything crazy with that. But the volume of this is something else. So let's figure out the volume of each one of these slices. So the shape of each of these slices is like a coin, AKA a cylinder. So the volume of a cylinder is pi r squared, and then we multiply by the height, but our height is very thin. In fact, we're going to call our height dy. So the volume of our slice is pi r squared dy, where r is the radius at our particular slice right here. All right, so we could put that into here. We have rho pi r squared dy gy. And then we could rearrange this. We have rho g pi r squared y dy. Now, normally we would just throw this into the integral and then do it, but there's a problem here. We have this as an extra variable. This is not a constant. If we move this up and down, our r is going to change with respect to y. So what we need to do is we need to get r is something with y's in it. So we have the wrong variable here. When did we have that happen before? That happened in the volume section, right? How did we get a relationship between r and y? I think I heard someone say it in the chat, or sorry, in person, but then now the chat's saying it. We use similar triangles to do it. So if we take a look at the side view here, here's our overall cone. So remember, this has a radius of 2 and then a total height of 4. Now let's say we're part of the way down here, or let's say we're down here. This is going to have a distance y from the top, and it's going to have a radius r right here. So since these are similar triangles, this bigger half triangle and the smaller half triangle, we know that 4 over 2 is y over r. So what we could do is we can cross multiply here, and we get that r is going to be y over 2 right here. So sometimes we need to use similar triangles for other problems besides the volume ones. So with this knowledge, armed with that, we could take that and put it in here. So we have 1/4 rho g pi y cubed dy. So remember, I'm squaring this, so I have y squared times the y we already have to be y cubed. And then I'm squaring the 1/2, giving me a 1/4 here. And now everything is right with the world because we have all of these constants and then we just have y's here. So now we're good to go in terms of the integral. So my total amount of work will be the integral of 1/4 rho g pi y cubed dy. And then let me ask you guys again, what are the bounds going to be for this? So remember, it's filled up to a height of 2 here. It's going to be from 2 to 4, just like the last problem was. Because remember, if we start at y equals 0 at the top here, we need to go down 2 before we start seeing any water at all. Then we keep going, and then once we hit the bottom, we're at 4. So 2 to 4 is where the water is right here. Why is it 1/4? Because when I substituted in the y over 2, I squared it, and squaring a half will give you a 4. All right, and then once again, we have a nice easy integral here. So we integrate up here, be y to the 4th. We divide by 4, and 1/16. This goes from 2 to 4. Let's see. Shouldn't it be 1/12? Well, no, so we're right, well, this starts as a cube, and then it goes up to 4, and then we divide by a 4 right there. So then we have 4 to the 4th minus 2 to the 4th. All right, we have to deal with some kind of big numbers here. 4 to the 4th is 256. 2 to the 4th is 16. So we have 1/16 of 240. And if we simplify that, that will end up being 15. So we have 15 rho g pi joules. So that's a lot of constants there, but you can leave all of them in there. That's totally okay. You can leave all 3 of those constants in there. Why does y become cubed in the work equation? Because we have 2 of these y's being for the area or the surface area of our shape, and then 1 of the y's is the distance we're moving. So those combined make a y cubed. All right. So anyways, that's it for work right here. I'm going to post the solution to the one we skipped earlier. That one's kind of interesting. And then tomorrow, or sorry, not tomorrow, on Monday, we'll be going over a different application of integrals. So I will see you guys then.
Thank you.